Welcome to my lecture series on group theory. Today we are going to continue our discussion about permutations. And in this connection, we discuss composition of permutations. So assume we have two permutations. F, given in cycle form, is this 1, 4, 3, 2, 6. And another permutation G, given in cycle form by 1, 4, 6, 2, 5. And the task is to find the composition of these two permutations. So how do we find the composition of these two permutations? So G is given by 1, 4, 6, 2, 5, composed with 1, 4, 3, 2, 6. And we know that first we have to find the images of symbols under F. And we start with the smallest possible symbol here. So the smallest possible symbol here is 1. And we know that the image of 1 under F is 4. So the image of 1 under F is 4. And then we operate G on this symbol. So the image of 4 under G is, we see that 4 is mapped onto 6. And thus 1 is mapped onto 6 by this composition. And we write this as 1 is mapped onto 6. Then we start with symbol 6. And we find the image of 6 under F. So the image of 6 under F is 2. And then we operate G on 2. So the image of 2 under G is 5. And thus 6 is mapped onto 5 by this composition. And thus 6 is mapped onto 5. Next we start with 5. So we see that 5 is not present in this permutation F. And hence 5 is fixed by this permutation F. And then we find the image of 5 under G. And we know that 5 is mapped onto 1 by this G we can see here. And thus it completes our first cycle. Then we start with the next smallest possible symbol, which is not present in this cycle. And hence we start with 2. And 2 is mapped onto 6 by this mapping F. And then we find the image of 6 under G. And we know that 6 is mapped onto 2 by this mapping G. And thus 2 is mapped onto 2 by this composition. So the next cycle is 2. Then we start with the next smallest possible symbol which is not used. And we start with 3. And we know that 3 is mapped onto 1 by this permutation F. And then we look for the image of 1 under G. And we know that 1 is mapped onto 4 by this permutation G. And thus 3 is mapped onto 4. Then we look for the image of 4 under F. And we see that 4 is mapped onto 3 by this permutation F. And then we look for the image of 3 under the permutation G. And since it is not present in the permutation G, hence 3 is fixed by this permutation G. And thus 4 is mapped onto 3 by this permutation G composite F. And hence it completes our cycle form of the composition of these two permutations. This process can be summarized as in this strategy. To find the composite of two permutations written in cycle form, we proceed as follows. We start with the smallest possible symbol, say 1, and find the symbol which is the image of 1 under F. And then we find the image of that symbol under G and write the result, say A next to 1 is 1A. Then we start with symbol A and repeat the above process. That is, we find the image of A under F, and then we find the image of A under G and write that image of A under G next to A. And then we repeat the process until the next symbol found is 1. That is, we receive this first element again. This completes the cycle. Then we start with the next smallest symbol not yet placed in a cycle. So we start with the next smallest symbol which is not yet placed in any cycle and repeat the above process until every symbol has been placed in a cycle, and it gives the composite of 2 permutations. And we omit cycles containing single elements. We can observe one thing more. Assume we have 2 permutations as given in our previous example, F and G of the set 1, 2, 3, 4, 5, 6. If we find G composite F of these 2 permutations, then this is 1, 4, 6, 2, 5, composite 1, 4, 3, 2, 6, and we have computed this composition that it produces 1, 6, 5, 3, 4. What if we compute this F composite G? Then F composite G is given by 1, 4, 3, 2, 6, composed with 1, 4, 6, 2, 5. And we start with the smallest possible symbol here. It is 1. And since this is G, this is F, so first we find the image of 1 under G. And the image of 1 under G is 4. Then we find the image of 4 under F, and the image of 4 under F is 3. Hence, 1 is mapped onto 3 by this composition F composite G. Hence, the result is 1, 3. It starts from this point. And we can find the rest of the symbols, but from the first 2 symbols we see that G composite F maps 1 onto 6, whereas F composite G maps 1 onto 3. And thus in general, we have that F composite G may not be equal to G composite F. That is, the composition of permutations is not commutative. Next, we find the inverse of a permutation. Assume we have a set S and we have a permutation F on this set. Since this permutation is a bijection and thus it has an inverse. And we note that if inverse undoes what F does. That is, if F maps X to Y, then F inverse maps y to x. Thus, F inverse is obtained from F by reversing the direction of the disjoint cycles of F. For example, I have a permutation F given in disjoint cycle form is 1, 3, 4, 2, 5. Hence, in cycle form, this is 1. This permutation maps 1 onto 3. It maps 3 onto 4. And 4 back onto 1. And then we have 2, 5. It maps 2 onto 5 and 5 onto 2. To find the inverse of this permutation, what we do, we reverse the order. And hence, we have 1, 3, 4. So reversing the order means that 3 is mapped onto 1, 1 is mapped onto 4, 4 is mapped onto 3, and 2, 5. So 5 is mapped onto 2, and 2 is mapped onto 5. Thus, F inverse is equal to, we can see that 4 is mapped onto 3, 3 is mapped onto 1, and 1 is mapped onto 4. And here we have 5, 2. And once again, we can simplify this to 1, 4, 3, 2, 5. And this is the inverse of the permutation F. And we can summarize this as follows. So the summary is that we reverse the order of the symbols in each cycle. So number 1, reverse the order of the symbols in each cycle. And then what do? We rewrite each cycle so that the smallest symbol is first. As we have done in our previous case. That is, F was this permutation 1, 3, 4, 2, 5. Then what we did, we reversed the order of symbols. And reversing the order was, this was 4, 3, 1, 5, 2. And we rewrite such that the smallest symbol is the first, and hence this is 1, 4, 3, 2, 5. And this one is basically the inverse of F. And this can be verified as well, is if we compose F with F inverse, it should produce the identity permutation. And this can be written as 1, 3, 4, 2, 5 composed with 1, 4, 3, 2, 5. So we start with the smallest possible symbol here, it maps 1 onto 4 and 4 is mapped onto 1, and hence the net result is that 1 is mapped onto 1. Then we start with the next smallest possible symbol, so it maps 2 onto 5 and 5 is mapped onto 2, and hence 2 is mapped onto 2. The next one is 3 is mapped onto 1 and 1 is mapped onto 3 here, hence 3 is mapped onto 3. The next one is 4, so 4 is mapped onto 3 and 3 is mapped onto 4, thus 4 is mapped onto 4. The next one is 5 is mapped onto 2 and 2 is mapped onto 5, thus 5 is mapped onto 5, in which we know that this is the identity permutation, and this can also be verified that this is equal to F inverse composed with F. And with this discussion, we are now ready to define our main object, which is the permutation group. So if we take a set S, then the set of all permutations on this set is denoted by Sn. We denote the set of all permutations defined on this set S by Sn, and hence we have our first theorem. And it says that the set Sn of all permutations of the set is a group under composition of functions. And the proof, we have seen that the number one, the closure property, and we have seen that if we take any two permutations from this Sn, then their composition is also a permutation on this set, and hence the closure property is satisfied. Number two, associativity. We know that the composition of functions is associative. And number three, the identity. We know that the identity permutation E that fixes every symbol of S is an identity element of Sn. Is an identity element of Sn. And number four, we have seen that for each F belonging to Sn, we have F inverse belonging to Sn, and thus every element of Sn has an inverse. And with all this, we conclude that the set Sn of all permutations of the set 1 up to n is a group under the composition of functions. This group is called the symmetric group. The name of this group is symmetric group. In the next theorem, we will discuss that what is the order of this group. So let us see. And here is our main theorem. It says that the symmetric group has order n factorial. So assume we have a set S of symbols having n elements, and we try to find out all the permutations from this set onto itself. So what we do? We count that how many different ways there are to compute the bottom row of the two-line form of the permutation of this set. That is, we need to know that in how many ways we can complete this second row. And we know that to fill this first space, we can fill this with any of the elements from this set. So there are n choices to fill this space. There are n choices for this element. Once this space is filled, that is, this element has been assigned an image, this image cannot be used again because the mapping is 1-to-1. And hence, to fill this space, we have n-1 choices. And so on. Thus, for the last element, we have only one choice. And thus, the total number of choices that we have, that for the first element we have n choices, for the second one we have n-1, for the third we have n-2, and for the last one we have only one choice. And we know that this is n factorial. Thus, the symmetric group Sn has order n factorial. Thank you.